And unless we solve, we will never get to understand how this fellow comes. Anybody who is interested in the solution? Yeah? I'll give it to you. Okay, you can read it. But do read it if you're interested. Huh? Okay. Now, if the wave functions look like this, then let me write down some of those. So, n is equal to 1. So, n can vary. You know that n can vary from 1, 2, 3, 4, so on and so forth till infinity. Right? L goes from 0 to n minus 1. So this all these conditions also come from the solution. Okay. And ML of course goes from minus L, 0, 1 to plus L. This we have seen earlier. It comes from the previous solutions, and this condition that L can go from 0 to n minus 1 comes from this particular solution. Anyway, so let's have a look at some of these wave functions. So n is equal to 1, L equals 0. I am talking of the 1s orbital, right? So the 1s orbital happens to have a wave function given by, does everybody have this? No? This table, okay, I'll maybe put it up here rather than writing everything. So, the first wave function is 2 into z by a to the power 3 by 2 e to the power minus rho by 2. Rho to the power L, right? L was equal to 0. So 1s is n is equal to 1, L is equal to 0. Right? So rho to the power L is 0. Rho to the power 0 is 1, L is 0, and it is 2z by a. We've written a over here, not a naught, because this is a general solution for whatever given value of z, to the power 3 by 2 e to the power minus rho by 2. Which means it's a constant times an exponential decay. So my wave function would just look like that. Yes? Sorry, I forgot one thing. If I go back to this, rho to the power L. So if I look very close to the nucleus at very small radii, then if I plot the wave functions for L equal to 0, then the wave function would look like that, right? It's decaying. For L not equal, so this is L equals 0. For L not equal 0, that is L equals 1, I have rho to the power 1. So for very small distances, this would be a straight line to start with. For L is equals 1. For L equals 2, it should be a parabola. For L equals 3, it should be a cubic equation. So what it tells me is that if I go to larger values of L, they have, the wave function does not exist much at the nucleus or close to the nucleus. So the probability of finding the electron in a larger L subshell happens to be lower. Or in other words, this is something which you might have heard, that the penetration depth of the s orbital is the largest. Okay, so going back to this orbital, right, I see if I plot this wave function as a function of r, This is what it looks like. I'm sure somewhere we'll have the plots also. Yeah, this is what it looks like. The first one, top left, n is equal to 1, L equals 0, the 1s orbital. Except that it's not radius r, but it's rho, which is plotted over there. Okay. Coming back to the next orbital, so that is 2s, right? 2 comma 0. The wave function is given by 1 by square root of 8 z by a to the power 3 by 2 e, no, there's 2 minus rho to the power e to the power minus rho by 2. Okay. Now it's still 2s, so rho, the value of L is still 0. So the first term was rho to the power L, right? Rho to the power 0. That is still there. This is also a nice orbital. These are only radial wave functions, okay? I'm still not added the angular part. So these are only the radial wave functions, r of n comma L, which depend only on radius. Yeah, you see there is no angular dependence over here, no theta, no phi. Okay. Now, what I have something extra over here is this fellow, 2 minus rho. 2 minus rho is a polynomial, right? The 2 minus rho is going to take the wave function up, or actually down. There's a negative rho. So the negative rho is going to take it down, and e to the power minus rho is then going to bring it back again. That is a decay part, but it's a negative, there's a negative sign over there. So the wave function would look like, again it's not 0 at the origin, right? So it would go down like this, and somewhere, see, e to the power minus rho, again it will have rho to the power 0, rho to the power 1, rho to the power 2, all these things. So it will finally win over the 2 minus rho polynomial and turn it around and take it to 0. Maybe look at a better diagram over there. This one, n equals 2, n equals 0. The bottom left. Okay. And if you see that it cuts y equals 0 at one point, right? How do I get that particular point? All that I have is 2 minus rho equals 0. This is the only one that cuts across. The rest of them, yeah, do not go to 0 at any other, I mean goes to 0 at infinity other than anything, nothing else. So this is the one, if you wish to find the position of the node, you use this, that is rho equals 2. And rho is equal to 2zr by na naught. So rho is equal to 2. In case of a hydrogen atom, z is 1, 2r by n, in this case is 2, a naught is equal to 2. Yes? Correct, or did I make any mistake? So R is equal to 2 times of A naught. Now, whoever was asking the significance of rho would definitely be getting it. It's being normalized by this A naught times the principal quantum number. Okay. Like Similarly, if we go to 3s, which would be 3 comma, no, before that there's a 2p also. How many radial nodes does this have? 2s, 1. You know that the number of nodes is n minus l minus 1. This is the number of radial nodes. The total